transformations. So here let us see the equations of canonical transformations. Equations of canonical transformations. So if we see in the case of several problems, we may need to change one set of coordinates. That means we have position coordinate and momentum coordinates. And if we may need to change one set of position and momentum coordinates into another set of position and momentum coordinates, suppose QK and PK. These are the old position and momentum coordinates. Small QK, small PK are the old position and old momentum coordinates. And here we are changing into another set of coordinates. That means capital QK and capital PK are the new position and momentum coordinates. So we have a relation between old and new coordinates. So here capital PK equals to capital PK into small p1 comma p2 comma so on comma pn comma q1 comma q2 comma so on qn comma t, and capital QK equals to capital QK into small p1 comma small p2 comma so on small pn comma so on q1 comma q2 comma so on small qn comma t. So these are the equation number 1, and these are the relation between old set of coordinates to the new set of coordinates, momentum and position coordinates. And here if there exists the Hamiltonian h dash in the new coordinates, actually we have the Hamiltonian h, and here in the case of new coordinates h dash we are considering as Hamiltonian. So pk dot equals to minus dou h dash by dou qk, and qk dot equals to dou h dash by dou pk. That is the equation number 2. So here h dash equals to sigma k equals to 1 to n pk qk dot minus l dash. Here L dash, it is substituted in the Hamilton's principle. We have delta integration L dash dt equals to 0. This is equation number 4. And this equation number 4, it gives the correct equations of motion in terms of new coordinates. That means capital PK and capital QK. Then the transformations in equation number 1, these are known as canonical or contract transformations. These are the equations of canonical transformations. Let us see example of the canonical transformation. Harmonic oscillator, it is the example of canonical transformation. So in the case of harmonic oscillator, Hamiltonian in terms of q and p coordinates can be expressed as h equals to half c q square plus p square by 2m. Here if you write p by m equals to omega square or c equals to m into omega square, we substitute c here in equation number 1, we will obtain h equals to half m omega square q square plus p square by 2m. Here we are replacing c with m omega square. So this is the equation h equals to this one. So multiply and divide with m for the first term of h. So here let us multiply and divide with m in only this first term. So what will we get? H equals to half m square by m omega square q square plus p square by 2m. So taking 1 by 2m as common from these RHS, from these two terms, we will obtain h equals to 1 by 2m p square plus m square omega square q square. So here by taking 1 by 2m as common, here we will obtain p square plus m square omega square into q square. This is equation number 2. Now let us consider the generating function, which is given by f1 into q1 q comma small q comma capital Q comma t, which is equals to half m omega q square into cot q. So this is the generating function f1 into q t equals to half m omega q square cot q. So we have h dash minus h equals to dou by dou t f1 small qk capital QK comma t. Let it be equation number A. Already this we have this existing equation. So by using equation number 3, this one and this one, we will obtain, we have small pk equals to 2f by dou qk, capital pk equals to minus 2f by dou qk. So from equation number 3, if we see, let us see here. Dou f by dou qk. So if we take the derivative of dou f with respect to qk, we will obtain. So here we have q term here. So half into q square, it is the derivative to q m into omega into cot q. So this is pk. So dou f by dou qk we have, which is nothing but pk. So from this equation number 3, we'll have dou f by dou qk equals to half 2m omega q into cot q. Or we can say dou f by dou qk, which is equals to this one, or pk. So 2 get cancelled. So p equals to m omega q into cot q. So from this one, we have p equals to m omega q cot q. Again, from the same equation, let us see capital Pk, which is equals to minus dou f by dou qk. So here we have q term here. So by taking the derivative for this equation number 3 with respect to capital Q, so we will obtain pk equals to minus dou f by dou qk. Already we have pk equals to minus dou f by dou qk. So derivative of d by dq into half m omega q square into cot q. So cot q derivative we have minus cosecant square q. So derivative of this one will obtain minus cosecant square q. So dou f minus dou f by dou qk equals to minus half m omega q square into cosecant square q. So minus minus get cancelled. So pk equals to dou f by dou qk equals to half m omega q square. So cosecant square means 1 by sine square q. We are replacing cosecant with sine square. So again from equation number 3, we have, if you see equation number 3, we don't have here any t term. T is not the time. So dou f by dou t equals to 0 and h equals to h dash. From 4c we have h equals to h dash, which is 4c. Now h dash we have h dash minus h equals to dou by dou t f1 qk, capital qk into t. So dou f by dou t, which is equals to 0. Dou f by dou t 0. So this term becomes 0. So h dash minus h equals to, so this term becomes 0. So let us see from this equation number 4b. From this we will find out the q. So from this term we'll obtain q equals to root of 2p sine square q by m into omega, or 2p by m omega. Sine square square root get cancelled for this term. So we will write in the outside the root. So sine q. So small q equals to 2p by m omega into sine q. Let it be equation number 5a. So substitute q in p. That means let us substitute this q in equation number 4a. Already we have this one. So let us substitute q here in equation number 4a. So p equals to m omega q cot q. This is equation number 4a. So p equals to m omega. So if you substitute q here, root of 2p by m omega into sine q. So here, if we substitute and make this solve, so we will obtain in root m omega, this m omega get cancelled with root of m omega and cot q into sine q. So if we are substituting this one here, we will obtain this one, p equals to root of m omega root 2p by m omega into cot q into sine q. We are replacing q 5a. We are replacing with q, this one. So small p equals to root of 2p m omega into cot means cos by sine. So we'll obtain here sine get cancelled. So now the transformation h dash is obtained from equation number 2 and equation number 4. That means from equation 2 and 4 we'll obtain. So here we have equation number 2, h equals to 1 by 2m p square plus m square omega square q square. And equation number 4 we have here p. So we need the transformation h dash. So h dash equals to h, because here these terms becomes 0, h dash equals to h also we have. So Let us substitute P and Q. So from equation number 2, we'll see. So this is equation number 2. 1 by 2m root p square plus m square omega square into q square. So let us substitute p value and q value from equation number 2. So h dash equals to 1 by 2m p square value. Let us substitute p and q values. So p this is, and q value already we have. So 1 by 2m. Substitute 1 by 2m. P means root of 2m omega whole square cos square q plus omega square m square root of 2p by m omega whole square into sin square q. So by substituting p value, q value in equation number 2, this is the required equation. Obtained equation. So this is equals to 1 by 2m. So here square and root cancel, square root get cancelled. So 2m omega p cos square q plus m omega into, here in root we have m omega. So if it come outside, so we will obtain here m into omega into 2p into sin square q. So taking common 2m and omega p. So here 2m omega p. Here also we have 2m and omega p. So by taking common, we'll obtain h dash equals to omega p into 2m. By taking common omega p 2m by 2m. So here we have cos square q plus sin square q. Cos square q plus sin square q, which is equals to value 1. So h dash equals to, so 2m get cancelled. So omega p. Equation number 6. So since Hamilton it is cyclic in q, that means if h is cyclic in q, conjugate momentum p is constant. So we know that h dash equals to E, which is constant energy. Already we know this equation. So from this one here, h equals to omega p. So if h dash equals to E means h equals to, we are replacing h with E. So E equals to omega p. So from this one, p equals to E by omega. Let it be equation number 7. So then equation of motion for q reduces to the simpler form. So let us consider equation of function. If equation of motion function q. So we have q dot equals to dou h by dou p. Already we know h equals to omega p or h by p equals to omega. So we are replacing h by p with omega. So q dot equals to h equals to omega p. H equals to omega p. So dou h means omega p by dou p. So here dou p by dou p get cancelled. We have q equals to omega. So with the solution we have q equals to omega t plus 5, where 5 is a constant of integration. So let us substitute 7 and 8. So a q value, equation number 8, and we have p equals to E by omega. Let us substitute 7 and 8 in equation number 5a. So we will obtain this is equation number 5a. Q equals to root of 2p by m omega into sin q. So this is equation number 5a. And p equals to E by omega. We substitute p equals to E by omega. Equation number this is 7. So let us see q equals to, p means E by omega. So 2 E by omega by m omega into sin. Q means omega t plus 5. We are replacing q with omega t plus 5. So q equals to root of 2e by m omega square. Here m into omega square sin omega t plus 5. So which is a customary solution of the harmonic oscillator. So this is the example of this canonical transformation, which is harmonic oscillator. Thank you, children.